Hello everyone, this is lecture 5 of week 10. Recall that in the past few lectures we were learning about affine scaling method, right. So that is an interior point method where you start with an interior point of a linear programming problem and converge to the solution, right. So, we ended with the steps of the algorithm, right. So, let me go through that once more before starting with an example, right. So, of course, the first step is to convert the given LP to its standard form, okay. So, that gives you A, B and C, right. So, yeah, this yeah, you can say gives A, B, C, right. So, you are minimizing C transpose x subject to x equal to B, x greater than or equal to 0, right. So, you have A, B and C. A is an M cross N matrix with rank of A equal to M, okay. So, and since it is an internal point method, we are actually initializing x 0 as an internal point of the feasible polytope. So, you might ask if I mean is there a problem if we take a boundary point or let us say a vertex for instance, okay. I mean so one of the questions is it a problem, okay. So, it could be a problem because we are having capital X 0 as a diagonal matrix consisting of X 0, okay, and X 0 is actually involved in inverses, right. So, yeah, you can see Y k is capital X k inverse into X k, right. So, if capital X k has zeros, okay, so that is actually a problem, okay, right. Of course, if you recall in simplex method what are the initial points that we chose, we chose vertices and most of our initial point was 0 0 0 0, right, all zeros for example. So, such a point is just not feasible here because yeah, if you choose your initial point to be all zeros, x inverse flops, right. So, yeah, since there is an inversion of x, right, not directly because we have only let us say A x squared A transpose the whole inverse, right. So, even if you have a few zeros, A x squared A transpose could still be invertible, but yeah, of course, you can understand the risks involved, right. So, that is the reason we usually do not choose x 0 as yeah, a point having zeros, right. So, we try to choose it as a point, yeah, which does not have zeros, okay, all right. And yeah, so these are k equal to 0 is fine. Yeah, this diagonal matrix is something that is very important for this method. This was not there in any of the methods that are discussed earlier, right. So, yeah, you construct a diagonal matrix consisting where the diagonal entries are the elements of the vector x 0, okay, and mu 0 is just the same formula that we had A x squared A transpose inverse A x squared C. So, we are finding mu initially because we first want to check if C transpose x k minus B transpose mu k, the difference between the primal value and the dual value is it within the tolerance, right. So, that is the reason we are starting with mu 0, right, fine. So, until this is yeah, the initializations you can say or initial computations, we go into the loop now. So, the loop only consists of centering, moving, yeah, movement is along a descent direction that also ensures that the resultant point is within the feasible set, right. So, you have centering, movement along the projection of the descent direction and decentering, right. So, in centering we are multiplying pre-multiplying with capital X k inverse, then yeah, we discussed why the direction has to be x k into A transpose mu k minus C. So, mu is the computation of mu is also useful here, please note that, and alpha k is the minimum of minus 1 by dj when I mean when you consider dkj actually. So, I will correct that too, it is minus 1 by dkj, okay, okay. So, yeah, that is actually to ensure that 1 plus alpha k dk is greater than or equal to 0. In fact, it should be strictly greater than 0. Okay. So, of course, we know what happens when it is when it could be 0, right. So, yeah, if you consider this, yeah, then you have alpha k dk is strictly greater than 1 minus 1, sorry. Okay. So, yeah, so one thing that you can see is if djk is positive, okay. So, alpha k, I mean, yeah, the step size is always positive, we choose the positive step size, right. So, suppose if yeah, djk is positive, this clearly holds, right, 1 plus alpha k dk greater than 0 always holds. The problem comes only for djk that are negative, right. So, if you divide by djk that is negative, right. So, the sign flips, because of which you will have alpha k is less than minus 1 by djk, okay, and this must hold for all j such that djk is less than 0. Okay. So, yeah, I cannot choose alpha k as equal to minimum of minus 1 by djk, right. So, it has to be slightly less. So, we will actually choose it as minus 0.9. Okay. Yeah, it just needs to be lesser, maybe you can also choose a higher number 0.95, 0.99 or something. Yeah, so 0.9 is something we usually choose, that is what that is how I am going to do the code as well. Okay. So, yeah, this actually constructs the movement, the direction and the step size. Okay. And in the centered feasible set, we actually do the movement 1 plus alpha k dk. Okay. And while decentering, we multiply by capital X k. So, it is capital X k into 1 plus alpha k dk. Okay. So, when you look at this as an algorithm, you can see that these two steps are not required, because you are not going to write them, right. So, because yeah, yk you are not using it anywhere, and similarly yk plus 1 as well, you can, instead of writing yk plus 1, you can just write it as 1 plus alpha k dk. So, we will actually remove these two steps. Okay. And yeah, x k plus 1 is just capital X k into 1 plus alpha k dk. Yeah, so now you need to get ready for the next step, right. So, yeah, since like you calculated x 0 and mu 0, you are calculating x k plus 1 and mu k plus 1 here. Okay. And yeah, so that is the whole algorithm. Okay. All right. So, we will actually work out some examples. Okay. We will start with the examples that we have already worked out for simplex method. Okay. We will start with our favorite example where the feasible set was a triangle with vertices 0 0, 1 0 and half half, right. So, yeah, if you recall that particular problem, so this is now we have examples. Okay. So, yeah, we minimize minus x 2, okay, sorry, x subject to, yeah, of course, you have the three conditions minus x 1 plus x 2 greater than or equal less than or equal to 0, x 1 plus x 2 minus 1 less than or equal to 0, and minus x 2 less than or equal to 0. But instead, yeah, we will write with the ax equal to b form, right. So, that was minus 1 1 1 1 0, 1 minus 1 1 0 1. So, you have x 1 plus, x 1 minus, x 2, x 3, x 4, and here you have 0 and 1, right, and of course, you want all of the x's to be greater than or equal to 0. Okay. So, you have capital A, which is what I have just written here, right, and this is little b, and c is 0 0 minus 1 0 0, right. Okay. And since this is the feasible set, right, so we should choose a point that is interior in the interior, right. So, because x 0 is an internal point. So, yeah, I suggest choosing 0.1 comma 0.05. Okay. Yeah, no particular reason, I mean it is just an internal point. Okay. So, but this has to be converted to this form x 1 plus x 1 minus and so on, right. So, yeah, x1 is x1 plus minus x1 minus. So, it is 0.1 0 and yeah, so this is 0.05. Okay. Now, x3, what is x3? Note that this equation has to be satisfied, x1 plus minus x1 plus x1 minus plus x2 plus x3 must be equal to 0, right. So, I mean I must give a feasible point. So, if the point must be feasible, then x3 must be computed, which is minus 0.1 plus 0.05, it has to be 0.05, okay. So, that you get minus x1 plus x2 plus x3 is actually 0, okay. And for the below equation you want 0.1 plus 0.05 plus x4 is actually equal to 1. So, that should be 0.85. So, 0.1 plus 0.05 plus 0.85 should be 1, okay. So, this is the x0 that we are going to give. So, with this I will actually write down the algorithm, okay, in Python. Okay. So, yeah, so this is a fine scaling, a fine scaling method. Okay, I will start by importing numpy as usual, and A is, yeah, so np dot array of minus 1 1 1 1 0 and 1 minus 1 1 0 1, okay, and B is 0 comma 1 and C is 0 0 minus 1 0 0, okay, and X we just mentioned that it is 0.1 0 0.05 0.05 and 0.85, okay, fine. So, the first two steps are done. We have converted LP to its standard form and initialized x0 as an internal point. Now, k equal to 0, x0 and mu 0 are the next steps. We will write that down. K equal to 0, capital X is just np dot diag of x, okay. So, it becomes a diagonal matrix, and yeah, mu is np dot linalg dot inv of A at x at A transpose, okay. So, A x squared A transpose, okay. So, note that we cannot use asterisks because yeah, that does element wise multiplication, at is the matrix multiplication, okay. Yeah, so with this you have to multiply A x squared C, right. Yeah, so this is mu, okay. So, given that yeah, so we will first print this because we want these values k x, and yeah, you can, yeah, possibly for the first one we will print mu, or yeah, we can print the modulus of C transpose x minus B transpose mu, okay, fine. So, while, yeah, this absolute value whatever we just wrote C dot x minus B dot mu is, yeah, is greater than tolerance. Tolerance is 1e minus 6, which you usually give, right. So, now, yeah, so the first step is, so I mean we have crossed out yk. So, we have only dk, dk is xk into A transpose mu k minus C. So, you have d into d is actually x at A transpose mu minus C, okay. Yeah, and alpha is minus 1 by sorry, minus 0.9 by okay. So, here there is a catch. So, we have to first find the j's for which djk is less than 0 and find yeah, that djk where minus 0.9 by djk is minimized, right. So, I claim that it is sufficient to write this. Okay. Okay. So, that is I mean I claim that both of them has the same purpose, because I mean I can explain it with an example. So, say you have D as a 4 dimensional vector, which is 4 5 minus 4 minus 5. Okay. So, you will only choose minus 4 and minus 5, and you have to choose alpha as the minimum of minus 0.9 by minus 4 comma minus 0.9 by minus 5, right. So, maybe I will write it slightly left. Alpha is min of minus 0.9 by minus 4 and minus 0.9 by minus 5, that is just min of 0.9 by 4 by into 0.9 by 5. Okay. Yeah. So, the minimum actually is 0.9 by 5, right. So, since 5 is greater than 4, 1 by 4 is greater than 1 by 5. So, it has to be 0.9 by 5, okay, which is actually minus 0.9 by min of d, right. So, min of d is minus 5, right. So, yeah, the quantity what I have written here, right. So, that is actually equivalent to minus 0.9 by min of d, right. So, yeah, proving this is also not very difficult. I mean it just involves positives and negatives. When you divide, you have to say inequality needs to be flipped, either from less than to greater than and greater than to less than. So, I will leave it for you to work it out. Okay. But nevertheless, both of these are the same. So, that is the reason I am actually writing it as alpha equal to minus 0.9 by minimum of d. Okay. So, yeah, I have got this dk and alpha k done. Now, xk plus 1 is capital Xk into 1 plus alpha k dk. Okay. So, note that capital Xk into 1, so capital Xk is a diagonal matrix with yeah, it is a diagonal matrix with elements of xk in the diagonal. So, when you multiply with all ones, you get back xk, right. So, yeah, capital Xk into 1 is just little xk, okay, plus. So, yeah, this will be yeah, alpha k into yeah, it is actually the element wise multiplication of xk and dk, right. So, it is a vector, but an element wise multiplication of xk and dk. So, that is xk plus 1 of I will be possibly I will write it like this, xk plus 1 of I is xk of I plus alpha k into xk of I dk of I. Okay. So, that is how it turns out to be. So, if I write it in the vector form, I will write it as x equal to x plus alpha into x into d. Okay. So, when I write x into d for 2 vectors, right. So, yeah, it does element wise multiplication. So, that is what we want, right, fine. And yeah, now we need to write capital X and mu like what we did here, right. So, yeah, I am just going to copy this down because there is nothing fancy. Okay. Yeah, just that we need to indent the mu. Okay. All right, and k equal to k plus 1. Now, we will print k x and np dot sorry abs of c dot x minus b dot mu. Okay. All right. So, yeah, I hope this would work. Let us check. Okay. So, here is the answer 0.5, 0, 0.5, 0 and 0. Okay. And yeah, so that is supposed to be the answer, right. So, x1 is 0.5 and x2 is 0.5, that is where we maximize x2. Okay. So, yeah, fairly straightforward, given that we have the algorithm done here step by step. Okay. So, but I would like to do one more thing. Okay. So, I would like to actually plot the trajectory of the points whatever we have got here. Okay. So, I want to show you that the trajectory of the points are actually in the interior. So, we started with an interior point 0.1, 0.05, right. So, I want to show how the trajectory of the points move here, okay, before we reach 0.5 comma 0.5, right. So, let me go ahead with the plotting library matplotlib dot pyplot, right. So, it is long time since we used it, but yeah, we will come back to it now. Okay. So, the first part that I have to do is to plot the feasible set, right. So, the feasible set consists of x1 greater than or equal to x2, or in fact x1 equal to x2 line will be there, and the other line is x1 plus x2 equal to 1, right. So, I will plot those two. Okay. So, yeah, let me say T1 is NP dot a range of 0 to 0.51 in steps of 0.01, okay, and T2 is 0.5 to 1.01. So, yeah, we need to write 1.01 because the last one is not counted, right. So, yeah, so for the first part is x1 equal to x2. So, I will plot T1 and this also T1, okay, and for T2 it is 1 minus T2, okay. Yeah, and then we will have to plot something else, but I will first to show you how this looks like, and then yeah. So, nothing much. So, we just have this triangle. Of course, we can also draw this, but I am refraining because yeah, you can imagine, okay. All right. So, fine, yeah, now we need to get hold of the trajectories, right. So, x is written as 5 dimensional vector, right. So, the vector that we need is yeah, it is x of 0 minus x of 1, right. So, that is the first point, and x of 2 is the next point, right. So, x of 0 is x1 plus and x of 1 is x1 minus. So, x1 is actually x1 plus minus x1 minus, right. So, that is the reason I have written it like this, and yeah, x2 is x of 2. So, that is the first point, and yeah. So, here I will I actually have to insert, okay. So, no, it is okay, array can be there, but yeah. So, I will append actually because it is going to be added at the end, right. So, yeah, fine. So, yeah, at each step I am appending x of 0 minus x of 1 and x of 2, okay. So, yeah, and let us append it to the row, okay. So, that yeah, it does not put it as one full column, okay. All right, and so here I should write y of 0 comma y of 1, okay. All right. So, let us now check. Yeah. So, I will first check if the shape of y is correct. Yeah, it is 10 comma 2, but I am so fine. Yeah. So, I have to plot the first column and sorry, the 0th column and the first column of y, okay. So, fine. Yeah, let me check now. Yes, okay. So, yeah, note that the blue and the orange curves are representing the feasible set of the problem, right. So, feasible set of the LP, right, and this the green line is actually the trajectory, okay. So, we started at 0.01 sorry 0.1 0.05, right. So, yeah, so you can see that this is 0.1 and this is 0.05. It moves yeah, very close to the line x1 equal to x2, and from then on it moves kind of parallel to this line and then reaches the point half comma half. Okay. So, you can see that it is completely in the interior of the feasible set, right. So, I mean if you want to visualize that in a much better way, because here it is like very close to the boundary. So, you are, I mean it does not appear as if it is in the interior, but if you want to visualize that very clearly. So, let us actually give the point 0.5 or maybe 0.45 if you want, 0.45 comma 0.05. Okay. So, but these will change. So, yeah, this will be 0.4, right. So, that you have so when you do Ax, right. So, you have to get equal to B, you should not get less than B or greater than B or whatever, it has to be equal to B. So, yeah, make your x3 the vector in such a way that Ax is equal to B. Okay. And yeah, when you do this you have 0.5, this has to be 0.5. Okay. Fine, let us see how yeah, with this initial point. So, this is also in the interior as you can see, right. So, let us check how what happens to the answer. Okay. Yes. So, yeah, we started with 0.45 comma 0.05, you can see that how it goes, right. So, yeah, it is completely in the interior, no questions on that, right. Okay. So, yeah, now that we have the feasible set very clearly laid out, right. So, we can also try a few other objective functions, right. So, we are minimizing minus x2 or maximizing x2. So, suppose if you want to maximize x1 instead. Okay. So, I can change the point very easily, right. So, I mean change C very easily to -1 comma 0, right. So, the answer is 1 comma 0, no questions on that. So, let us see how the trajectory behaves now. Yes. So, yeah, it kind of moves parallel to the horizontal line here, right. So, where it is x2 equal to 0, right. So, it moves parallel and then moves to 1 comma 0. Let us check what happens to the other initial point that we were working with, 0.1, 0.05, 0.05 and 0.85, right. So, yeah, the objective function is maximize x1. Okay. So, yeah, okay. So, it moves here and then gets back to 1 comma 0. Okay. So, yeah, the reason why I am showing all this is to show that the trajectory is clearly in the interior of the feasible polytope, and yeah, I mean it never, in fact it never touches the boundary either, right. So, it touches the boundary only when you reach the solution. Okay. So, that is the name, that is why the name interior point methods. Okay. So, yeah, in the beginning week of the next lecture we will also look at a few more examples, okay, before we close the discussion on affine scaling method. Okay. Yeah, so it extends to the next week, but I think it is fine. Yeah, we will see a few more examples in the next lecture. Thank you.